Section 6.4, there's a lot of information in here. Some critical information, understanding trigonometric ratios and finding angles of those ratios. We're going to take a look at two special triangles, or known as our special right angles or special right triangles. And some of these we'll be able to do without a calculator in terms of finding values, and some of them we'll use a calculator. But this part of the trigonometry section of chapter 6 is a big one. It's a key one. So got to unpack a lot of material right now. First of all, let's kind of get familiar with our relationship between these angles, theta, and then the relationships that result from triangles that may be created. There are 4 places along this circle here where point xy will be on an axis, positive x-axis, positive y-axis, negative x-axis, negative y-axis. And at that point, we have some unique situations that happen with regards to our sine, cosine, tangents, and our reciprocal functions. But first, let's just take a peek here at a little description. So, reminder, we've got an angle theta, and remember that our angles are always going to turn positively in a counterclockwise direction. And they're going to go negative in a clockwise direction. And they always start from the positive x-axis. So when we're talking about finding the ratio of some angle theta, we're coming from this 0 point. We're going to also talk a little later on in this section about a different angle. It's also known as a reference angle. And sometimes that reference angle, if this angle happens to be in quadrant 1, it will be the same thing as theta. But in quadrants 2, 3, and 4, it's different. So we'll talk about that when we get there. So we have this point xy, and this point is somewhere along the outer edge of this circle, along its circumference. And when you're at some point on the circle, you create a coordinate, and that coordinate has an x value, and then that coordinate has a y value. And we've already talked about how if we look at the sine of that theta angle, sine would be y over r, and cosine would be x over r, and tan would be y over x, and then all of the reciprocal functions would result from that. Let's get a little visual going on here of this concept of this triangle that's created. In the next section, we're going to talk about something called the unit circle. And the unit circle is a circle with a radius of 1. And you'll notice how this unit circle is in this diagram here, that we have these 4 points that we highlighted earlier, the points that are on the axes. These are called quadrantal angles. And notice what their coordinates are if you have a radius of 1. So if I'm to the right from my origin of my unit circle, right there, and I'm 1 to the right, that means the length of x and the radius length become the same thing. And if the same thing happens where I'm now at the top of my circle, now the radius of 1 becomes the same thing as the length of y. And so we have just these coordinates that we think about at those specific quadrantal angles. But what I wanted to show you was this idea of this triangle. So here we're going to drag this point around, and as we do that, you're going to notice 3 things that are changing. The red number is your x value, the blue number is your y value, and then you have your degree, the yellow, greenish looking thing. And you'll notice that we create a right triangle, and the right triangle always has an angle that's coming from the center of the circle, and that angle will always be referencing the x-axis. And you'll notice that the radius of the triangle, the 1, which is also the hypotenuse, radius of the circle and the hypotenuse are the same thing. That never changes. It's always positive. Radii of a circle are always positive. So we're going to drag this thing around. Look what happens. So I get these points. You notice my triangle changes. And there are some places, like right there, almost there, right there, close enough, where what has disappeared is the y part of my triangle. It's now essentially, well, it is 0 right there. And the x part of my triangle, the red, -1, is the same as the r part. We just talked about that. And then we go, and let's say we're going to land here. Well, now what has disappeared is the red part of my triangle, which is the x, measuring x, and the blue part is -1, which is the same thing as the radius. And you'll notice the theta angle is that green angle. Notice it always turns from 0. Get back there. No triangle on positive x. So 4 unique places, triangle does not exist. And those are the ones that we're going to have to be careful of. Those are our quadrantals. But this is the idea of talking about how when I move around this unit circle, I create these different relationships between x and y, thus giving me different answers for all the trig functions. So you can play around with this and kind of get an idea of what's happening. Pay attention to the fact that my values, the x and y values, like in this case where I've stopped right here, they're both negative. And if I were back up here in this quadrant, you'll notice the x's are negative and the y's are positive. And then what about over here in quadrant 3? Well, now my x's are positive and my y's are negative. And in quadrant 1, you notice that both x and y are positive. So keep that in mind when we talk about our quadrantal angles and our reference angles. Okay. So then here were all of our relationships. We had expressed sines and cosines in terms of a right triangle where we had an opposite side, an adjacent side, and a hypotenuse. And now what we're going to do is, since we're going to kind of think about circle, the unit circle, we're going to be changing these O's, H's, and A's into X's and R's and Y's. And you'll notice that in the sine of the theta for this given triangle, the O, the opposite side, is y. That's the side across from the angle theta. And the H is now replaced by an R. So O's become y, H becomes R, and in the cosine world, we notice that the x, which is our adjacent side, there's the relationship between those. So start thinking y's, x's, and r's when you're talking about your trig functions. Quadrantals, those are these angles that land on the axis. So 90, 180, 270, 360. And we're going to see, we already saw visually what happens. The triangle disappears, and we understand what parts of the triangle disappears. So let's take 90 degrees, where we're sitting right here. And if we remember from the unit circle, the diagram prior to this, we were at point 0, 1 right there, where I had an x value of 0 and a y value of 1. So what we do with this is we can use those values of y and x. And I also remember that r is equal to 1 for this unit circle. And if I had a sine which measures y over r, well, at that particular point, our y value is 1 and our r is 1, so sine of 90 would be equal to 1. What would the cosine be? Well, the cosine is an x over an r, and you'll notice at that point, my x is 0, my r is 1, so now we have cosine of 90 is equal to 0. Tangent. Tangent is a y over an x, where we have a 1 and a 0. Now we can't divide by 0, so that's undefined. Cosecant, the reciprocal of a sine, is a r over a y, a 1 over a 1, which is 1. Secant, the reciprocal of a cosine, r over an x, a 1 over a 0, also undefined. And the cotangent, the reciprocal of tangent, x over y, giving me 0 over 1, which is 0. So all of that happens at 90 degrees. understand this relationship between the x's and the y's and the r's, it actually isn't all that bad. Let's just go ahead and put the numbers together with these other ones, knowing we're in different locations now. So a 180 angle, remember what we're doing is we're turning theta from 0. So we're now over here. And let's say -1, 0 coordinate-wise. So we fill all of our information in for sine. We know y over r. 0 over 1 is 0. Cosine x over r, -1 over 1 is -1. Tangent y over x, 0 over -1. Cosecant r over y, so we have 1 over 0 is undefined here. Secant r over x, 1 over -1. And the cotangent x over y, -1 over 0, undefined. All right, flipping over now to the 270 world, the 360 world. What happens here? So 270, we're now putting ourselves down here. Coordinate-wise, you're at 0, -1. What happens here? 270 sine is -1. Y over r. Cosine is going to be a 0 again. Tangent is going to be undefined again, just like it was for 90. Cosecant is going to be -1. The secant is going to be undefined. And then our cotangent will be 0. So why on 90 and 270 is this the case? Or, well, what happens on 90 and 270 is my x's become 0 and my y's either become +1 or -1. So you can see a little relationship there. And then lastly, 360. Down there, and that has a coordinate of 1, 0. So what happens out there? Sines are 0. Cosine in this case is 1. Tangent y over x, 0 again. Cosecant is undefined. A secant is a 1 and a cotangent. X over a y is undefined. Alrighty. So those are our quadrantal angles. 1s, 0s, -1s, or undefined. And notice the ones that are undefined are going to be our tangents, our cosecants, or our secants. That's because we're dividing in some cases by 0, where with sines and cosines we're not doing that because our r value is always 1 for a unit circle. All right, so here, big concept here to understand is this idea called a reference angle. A reference angle is an acute angle, so it's between 0 and 90, that is formed by the terminal ray of theta and the x-axis. So let's refresh what happens here is our initial ray is in standard position. Our initial ray is hanging out on the x-axis, positive x-axis. And what we're doing is we're turning an angle of theta to get to what we talked about as our terminal ray. Remember, the terminal ray is the ray that has the same start point as our initial ray at the origin, but just lands somewhere else. So this is an important concept, understanding where theta is always coming from. It's always coming from positive 0, which is on the right-hand side, the positive x-axis. The alpha, which is our acute reference angle, does not measure from theta, or from 0 degrees. It's always going to measure from the x-axis back to wherever the terminal ray is. So in quadrant 1, from the initial ray to the terminal ray, that distance, or that angle rotation right there, is our alpha. And you'll notice that theta and alpha are the same thing in quadrant number 1. So we're going to generate some rules that can help me find either theta or the reference angle alpha if I've been given one or the other. So our rule here, quadrant 1 rule, is that whatever my alpha is also my theta. Again, alpha is our reference angle. Okay, what about quadrant 2? So now what we've done is we turned an angle theta from 0, and you'll see that we've been left with an angle that measures from the x-axis back to that terminal ray. There's our alpha. And how would we find the alpha if we knew what theta was? Well, in quadrant 2, the alpha would be the leftovers from 180 degrees, which is, again, right there. Remove from that the theta angle that we've turned, and we get our alpha. So there's our rule in quadrant 2, that our alpha is equal to 180 degrees minus theta. Now we could also be expressing this in terms of radians. So I could write this as pi minus theta. Well, what if I wanted to find theta because I knew what my reference angle was? Well, we just take that same equation and we solve it for theta. And if I did that, I'd have 180 minus alpha is how we could find theta in quadrant 2. All right, then we keep going here. So now our new quadrant 3 angle, look at this, we spin all the way around. Now we're there. And I typically refer to these as, if I'm in the second quadrant, I'll call theta 2. If I'm in the third quadrant, theta 3. If I'm in the fourth quadrant, I'll be theta 4. So we spun around. Now we're in quadrant 3. We see our reference angle measured from the x-axis to our terminal ray. And then we figure out, okay, how do I calculate one or the other? Well, in quadrant 3, we can say that our reference angle would be equal to theta minus 180 degrees, or theta is equal to 180 plus alpha. Again, one or the other. I'm either trying to find the reference angle alpha or I'm trying to find theta. And then lastly, quadrant 4's angle, we spin all the way around until we get over here. Call that quadrant theta 4. And once again, you'll notice the reference angle, positive angle that comes from the x-axis. We haven't really mentioned that before, but we're going to refer to a reference angle as an absolute value. So all of these have been calculated as being positive. So in quadrant 4, what's my rule? I would do, finding the reference angle, 360 minus theta. And if I wanted to find theta, I would just simply do 360 minus alpha. And there are 4 rules you're going to need to remember for either finding alpha reference angle or theta, the angle turned from 0. Now remember, we could also have negative angles, and all the negative angle rotation does is it just goes, instead of counterclockwise, it just goes clockwise. But our reference angles, alpha, we're always, again, be thinking about absolute values for alpha. because these angle alphas are the angles I'm going to use to help me with my trig functions. You'll notice, like we'll use the example here for quadrant 2, that at that angle alpha, I can create a triangle. And that triangle, we will always, from the end of our terminal ray, we'll always draw a line, vertical line, back to the x-axis. So there's my y value. And here's the x value of that triangle. So these alphas create for me this acute angle that I have coming from the origin for this right triangle. Here's the x values. So you'll see no matter where I am, I generate a right triangle Notice that some of my signs are positive x's, some of them are negative x's, depending on where I'm at. Quadrant 4, I have that y value, which is negative, and I have this x value, which is positive. So every time I put myself in a quadrant, I create these triangle relationships with x's and y's. All right, so let's find some reference angles. Given some angle theta, which is what all of these are. These are angle thetas. Let's see if we can go find out what our reference angle would be. It means we're going to be using our rules. So what we do is we first of all take the angle and we figure out where are we. So in the first example here, 120 degrees. Let's put this out of the way a little bit. Degrees is over quadrant 2, so we're just kind of estimating. There's our theta 2, because we're in quadrant 2 of 120 degrees. Just to kind of get ourselves going here, here's the triangle that results. And then we really don't need this to do the reference angles, but I want you to start thinking about triangles. And there is my angle alpha. The angle that I need to use to get back to the x-axis from wherever I am in whichever quadrant. And we know that our rule states that alpha is equal to 180 minus theta in quadrant 2. So we have 180 minus 120, or a 60-degree reference angle here in quadrant 2. What about the next one, 250? Well, that's in the third quadrant. So now we're somewhere down here. And again, we've turned an angle theta, and we're in quadrant 3, so I'm going to call that theta 3. What's the triangle that results? This one. It's real tempting to want to draw our triangle to the y-axis, but by definition, a reference angle is an acute angle from the x-axis. We have negative x values, we have negative y values, and here it's our alpha. And in quadrant 3, we know alpha is equal to theta minus 180, or 250 minus 180, which is 70 degrees. Notice I'm not writing them as negative. Our reference angles are always positive. Okay, these next ones. 340. Now we're over in quadrant 4. There we are. Quadrant 4. I'm going to not draw the triangle this time. Here's my reference angle I'm trying to find. And in quadrant 4, our rule states 360 minus theta is how we find our reference angle. So in this case, 360 minus 340, 20 degrees. And then lastly, be 70 degrees. There I am. There's my theta. We're in the first quadrant. We'll call it theta 1. And it just so happens that theta 1, because it's in quadrant 1, it's the same thing as my reference angle. And that's our rule for quadrant 1, that alpha is equal to theta, which means we have 70 degrees. Special right triangles. You've probably already seen these in geometry. But these right triangles have relationships between their sides that are always a ratio, a unique ratio. For example, on our 45, 45, 90 triangle, which is this one here, we have a 90-degree angle. And I've expressed these angles in both degrees and radians so that we can become more familiar with radians. We're probably least familiar with those. So let's start thinking in terms of radians. So we have a 90-degree angle and then two 45. Remember, the two acute angles of a right triangle have to add up to 90. So we have two 45s, which means we have an isosceles triangle here. And given the sides that we have here, the legs of the triangle each being the same, in this case being a 1. If I were to use Pythagorean theorem and do 1 squared plus 1 squared and get 2, and then take the square root of that to find c, I would find the hypotenuse is the square root of 2. And the sides of a 45, 40, 90 and a 30, 60, 90 are always in that same ratio with one another. Meaning, if I were to change the length of the legs on this right triangle, let's say we made the length of the legs 2. Well, then the hypotenuse must change proportionally as well. So 2 squared plus 2 squared is square root 4. 4 plus 4 is 8. So we have the square root of 8. Or we have 2 root 2's. You only need that equal sign there. So basically, whatever the legs are for a 45, 45, 90, you multiply that length by root 2, and that would be your hypotenuse. And the same thing holds true for the 30, 60, 90. If I were to change that 1, for example, on the 30, 60, 90, let's say we made this 1 a 2. Well, that would mean the hypotenuse is going to be double, which means it's a 4. And the other leg is always going to be root 3 times what the short leg is. So I'd have 2 root 3 if I changed the short length to a 2. So they're always in this relationship with one another. But we're going to focus on the given ones that we have 1, 2, and root 3 for the 40, for the 30, 60, 90. And we'll stick around here and focus on the 1s and the root 2's for the 45, 45. So what do we do with this? Well, these are our special right triangles that result from these specific angles. 30 degree, 45 degree, 60 degree angles. And with those angles, we actually don't need a calculator. We can just simply use the relationship from the sides of these triangles to help us find our ratio. Y over x is x over r's, y over r's. And so these would be like a non-calculator problem that you might see on a quiz or a test. And that's what we're going to do here. We're going to find out what are the exact values, meaning in this case, when I say in this problem, what are the exact values? I am asking you for the ratios. So in this case, for problem A, I have the angle theta, which just happens to be, in radians, 7 pi over 6. So sine of an angle is equal to a ratio. And so we are looking for that ratio value. All right, so just remember, whatever is coming after these sine, cosines or tangents in our trig function is an angle, and we're trying to find, in this case, the ratio value. So what do we do with 7 pi over 6? Well, first thing we do is let's go ahead and figure out where are we with an angle of 7 pi over 6. So we do a little sketch. I'm always going to be a big proponent of drawing a little sketch of where you're at. So a little refresher on radians. So we have 0 radians, pi over 2 radians, pi radians, 3 pi over 2, and then back to 2 pi or 0. So 7 pi over 6. Remember when we were talking radians initially, we talked about how the denominator can help you figure out what your angle is, because the denominator is splitting pi into that many equal parts. So when we divide by 6 for radians, that means we're talking about 30-degree increments. So we took this 0 to pi and we broke it into 3 parts, 1, 2, 3, and then we kept going so we get 6 parts out of it. There are 6 equal angles that would create pi. So pi, in terms of sixths, pi is the same thing as 6 pi over 6s. Here's the first pi over 6, and the second pi over 6, and the third pi over 6, and so on until we work our way around here. All right, so what we've done is we've gone 6 pi over 6s to get to this place of pi, and we're adding another pi over 6. So we're adding one more. And that is 7 pi over 6. So we are trying to find out what is the ratio created by this angle. All right, so we figure out where we are. We are in quadrant 3. Let's erase some of this stuff so we can take a look at our triangle. So we're in quadrant 3. Over here somewhere, and there's the angle that I've turned, and I've created this triangle. And in this triangle, just going off origin again, I have a negative x part of the triangle. I have a negative y part of the triangle. Then I have this angle here, and there's my reference angle. So we've spun around 7 pi over 6s. Remembering that 6 pi over 6 is right here. So what do we do to figure out what's our leftovers? Well, we were working with our reference angles in degrees. Let's try it in radians now. In quadrant 3, we said that our reference angle in degree was always going to be theta minus 180. Well, now we're in radians. So really we have theta minus 180 is pi. So our reference angle then is 7 pi over 6 minus pi, but we want to have common denominators, so we know that pi is the same thing as 6 pi over 6. And so now we have a reference angle of pi over 6. All right, so we have a pi over 6 reference angle. We go and we take a look at the triangle that has a pi over 6 reference angle, and we would see back up here that a pi over 6 reference angle is the same thing as a 30. So we're talking about a 30, 60, 90. So we figured out where we were, quadrant 3. From that, we drew our triangle, and we labeled our sides, in this case, generic x's and y's, and we used negative x and negative y. We're actually going to put the right triangle relationships in here from our 30, 60, 90. So our 30, 60, 90 triangle, this is what we just need to remember, that across from the 30 degree is always the smallest side, which is the 1. And across from 60 will always be square root of 3. So if we were to take that 30, 60, 90 triangle and plop it right here into quadrant 3, then we would have across from our theta, or our alpha, which is a pi over 6, we would have a length of negative 1. And our radius for a 30, 60, 90 triangle would be this 2 value. And even though we don't need it, we'd have the x part of the triangle for the 30, 60, 90 is right there. It was square root of 3, but it's negative because we're going to the left. So from that information then, I can answer what is the sign, or what's the y over r value of this 7 pi over 6. The y is a negative 1, and the r is a 2. So the sine of 7 pi over 6 has the ratio of negative 1 over 2. Cannot forget this. All support the covers. So looking in quadrant 3 with the t meaning that tangent, cotangent are positive, that means in quadrant 3 that the signs should have been negative, and that's what we found. The sign is negative down there. All right, let's go try this with B. We're in the same location, so we're not going to redraw our triangle here. We're still at 7 pi over 6, but now all we need to do is just relate it to the x over the r. And in this case, you notice our x is a negative root 3, and our r is a 2. So a cosine of that same angle, still in quadrant 3, is a root 3 over 2. And that is because what happened there is our 30-degree angle didn't change, but what did change was our relationship of our sides. We were looking at x's instead of y's, and so we used the square root of negative, or the negative square root of 3 there, and we came up with that value. And again, quadrant 3, cosines are supposed to be negative, and that's what we found. What about 120? All right, let's do this again here. Then I'm going to see if you guys have noticed some steps that we've taken here. We keep kind of doing the same thing. So the first thing we do is we locate where we're at. 120 degrees, right there. There's 120. That's the first thing we locate. The second thing would be we look at our triangle that results. And there's our triangle. Then we would consider what our reference angle is. All right. Quadrant 2, our reference angle is always 180 minus theta. So we have a 60-degree reference angle right there. There's our alpha, 60 degrees. All right, what would we do next? So we figured out where we were. We drew our triangle. We figured out our reference angle. Now we go back and look at our 30, 60, 90, or 45, 45. This is a 30, 60, 90. And the angle that we are at is a 60, which means across from the 60 is our root 3. Hypotenuse, r, still a 2 here. And negative 1 on the x part of that triangle. So again, we're using our right triangle relationships for 30, 60, given the angle alpha, put our triangle ratios, or the lengths of our triangles together to help me find my ratio. And then now we can answer the question of what is the tan of 120. The tan of 120 is a y over an x value. And in this problem, a y happens to be a square root of 3, and x happens to be negative 1, so we get a negative. And again, thinking about all support the covers, right in that quadrant 2, tangents are negative. So we're obeying our little acronym that helps us remember what values our sines and cosines and tangents and all those guys are. And there we have it. So why don't you guys take a shot here at D and E, and then we'll come back and check to see how you do. All right, here are your answers for D and E. I've also listed on the right-hand side those steps that we mentioned. Draw your angle. From that angle, draw your resulting right triangle. Remember to always, from your end of your terminal ray, draw a line down to the x-axis. From there, find my alpha. Figure out which triangle you have, a 30, 60, 90, or a 45, 45, 90, and then find your ratio. And here are the answers for D and E. And then lastly, we have, let's find the smallest angles. So in this part, we're just basically going the other way. We're not looking for the ratio. We've been given the ratios. So here in this example, we've been given y and we've been given r. So we're going to, from that, find out what angle, or in some cases, angles, I would have that produce this ratio for this triangle. So it's the same kind of a concept. From the ratio, figure out what triangle you might be using and where you are. So first of all, let's notice this, that in A, I have a positive ratio of √3/2. And simply remembering all support the covers. That means I'm going to create sine positively in quadrant 1 and in quadrant 2. So I'm going to have two angles here. So let's figure out the triangles that result. Have our little diagram, make it a little bigger this time. We have that angle right there, call that one θ1. And then we're going to have another angle over here we will call θ2, because that's what quadrant I'm in. Those are the two angles that we're looking for that produce this ratio. So from each of these we create our triangle, right? There's our y parts of our triangle. And those would be √3s according to our ratio of what we've been given. And then we have the x part of our triangles. We don't know those. And we have the radius part of our triangles. We know those are both 2 there. I really don't need the x to be able to answer the questions. So what I have to find is what was the reference angle so that I know which triangle to go back and refer to. What was the reference angle that created these? So again, there's my reference angle in this first triangle. Here's the reference angle in the second triangle. They're the same thing because they produce the same ratio or the same triangles, but just in different quadrants. So, well, what we do is we figure out, look at our triangle. And let's concentrate on this triangle here on the left. So we're going to take a look at this triangle. It's the same one that's going on the right, but we're going to pull it out. And I'm trying to find that. I know that's a √3, and I know that's a 2. So we got to go back and think about our special right triangles. What is the one that has the opposite side as a √3? What's the angle? So there's my opposite side that's a √3, and my hypotenuse, or my radius, is 2. Well, it's the angle across, right? So I'm talking about a 60-degree angle is producing this relationship. That would mean my alpha has to be a 60. And if that's true, then in quadrant 1, we know our quadrant 1 theta is the same thing as our alpha. So we have a 60-degree angle there. But what about quadrant 2? Well, in quadrant 2, we said we can find our alpha by doing 180 minus our alpha. And in that case, we have a 180 minus 60. So theta 2 is 120 degrees. Those would be your two angles that produce a relationship of positive sine of root 3 over 2. So we're kind of working the same process that we did when we were looking for the ratios. Where am I? Based off of the positive or the negative value of the sine. So I was in quadrants 1 and 2. I drew a generic terminal ray and a generic theta in those two quadrants to help me create my triangles. Then from those triangles, knowing that I have the relationships that were given to me, I draw those sides, either the x, y's, and r's on the appropriate parts of the triangle, and then figure out what my alpha or my reference angle is from that. Let's real quickly, let's try one of these reciprocal functions. Let's try D. A secant related to a cosine. Cosine, in this case, of negative values. According to all support the covers, this is going to happen in quadrants 2 and 3. So we have now an idea of our triangles. Secant is an r over an x. So we know our r is 2, and we know the x's in both of these triangles happen to be a negative root 3. Remember, my r can never be negative, so I know that that negative 2 over root 3 ratio means that x has to be negative. So what was the angle that we're looking at? Well, we're looking for theta 2, but we're also looking for theta 3. Which means we need to find what in the world are these reference angles. What are those alphas right there? All right, so once again, I've got my little sketch. I know where I'm at. I know the angle I'm looking for. I have a side that maybe I want to find, or I don't need the side. I'm at an angle that has an adjacent side, or an x side over root 3. Across from this angle, this side over here, or this side over here, in a triangle that has this relationship of a 2 and a root 3, well, we're missing the 1. So I know that I have 1's, one of them positive, one of them negative on those triangles. And what is the angle across from a 1? Well, we know that's a 30. So according to my special right triangles, I now know that my alpha in this case is a 30-degree angle. So now I go find theta 2. Once I know my alpha, I can find my thetas. Theta 2 would be 180 minus 30, or 150 degrees. Theta 3 would be 180 plus 30, or 210 degrees. So those would be the two angles that produce a secant value of negative 2 over root 3. All right, and there's our process for finding the angles once we have been given a ratio.